Let me show you how to be a good Bayesian. Change your predictions after taking information in.
You had a very original origin story because you claim and you wrote actually that quantum physics actually turned you into a Bayesian. So tell us why. And I'm also curious if there are any key moments that shifted your perspective.
So yeah, we've been talking about quantum physics and not Bayesian statistics. So it all started when I was a graduate student and I was interested in this field called quantum foundations. So it's kind of really trying to understand the deep underlying questions about quantum physics. The problem is, if you dig deep enough, you find that quantum physics is just a kind of framework built on top of probability theory. You've probably heard of things like the uncertainty principle, things like that, or that quantum physics is a probabilistic theory. And if you look at all of the debates that happen at the fundamental level and the foundational level of the field, they have more to do with the interpretation of probability than they have to do with physics. So when I was a graduate student, I thought, well, I'm not going to be able to answer these questions until I understand probability. And I suppose in this podcast, I'm preaching to the choir, but I came out on the other side of that as a Bayesian. But like Bayesian, I would put in sort of scare quotes, because nowadays you can follow the recipes in a book that uses priors and Bayes' rule and it has the title Bayes on it without the need to actually have an interpretation of probability at all. So it was more like, in order to answer these questions and have a satisfactory understanding of what's going on in quantum physics, you need to have an interpretation of probability. For most physicists, it's just an implied interpretation that they don't really think about. But for me, it came out with this subjective interpretation, and that really helped me understand it. But then at some point, I was talking to my thesis committee, and they didn't like this at all. So most physicists, especially quantum ones, think probabilities are objective. So they told me to do something practical. So I transitioned and then tried to start to apply Bayesian statistics to problems in quantum physics, which, it's essentially just classical statistics with just unfamiliar models and different loss functions and complex numbers are involved in some sense. But yeah, it's basically just a way to derive a likelihood function. Once you have a likelihood function, then you're just doing classical statistics. It's just a weird likelihood function. So I was able to apply Bayesian statistics to problems in quantum physics. I started from this sort of philosophical point of view and then was told to do something practical. And so then I was able to do some practical things in applying Bayesian statistics, quantum physics problems.
Did that change the view that your supervisors had?
I think to some extent it did. So those techniques and tools that we developed, just 5-6 years later, became popular and now they're being used in the field, although it's still dominated with frequentist methods.
Yeah, in my experience, that's the same. So usually people I talk to came to Bayes through a practical concern. For instance, a PhD student who was completely blocked on her paper with the classic framework, and then she just tried Bayes because, well, that was one of her last resort and it solved all of her problems, and now she's just doing that. But that's a very practical motivation. And yeah, I see most people coming from that angle. You're actually more in the outlier side, where you've been more interested in the epistemological point of view and then shifted to actually doing it. And yeah, actually what I've seen is to convince people that it's actually useful, just show them. And then they'll be like, yeah, that does look good. And that does solve the problem we were having. So, why not try that? Yeah. So in my experience, that's been the same too. And I'm curious, when was that work you did on practical Bayesian inference? When did you do that?
That's got to be 12, 16 years ago. So it kind of culminated in, we built this tool, we called it Q-Infer, and it's basically a sequential Monte Carlo integrator that just naturally was able to solve the kinds of problems that people have in quantum physics. So because it's quite difficult actually to use standard tools, often they don't play nice with complex numbers and things like that, don't naturally have the kind of loss functions and things that we use in quantum physics, kind of matrix manipulations that we have to do. So, and at the time there wasn't that many, right? Like computational Bayesian statistics is a relatively new thing. There was a few tools, but not many. And so we ended up building our own, and it's been used many times over the years. And that was maybe 10 years ago. I stepped back from that and handed it off to the next graduate student.
Yeah, that's why I asked you, when did you do that? Because just a few years ago, there wasn't a lot of tools to do that. So yeah, I'm guessing you had to write the algorithm from top to finish on your own, right?
Yeah, and honestly, sometimes it's better to do it that way. I mean, if you want to really deeply understand something, you have to build it yourself. We can't build everything from scratch. If you want to understand particle physics, you can't go build your own particle collider. But for things that you have the capacity to build, I would always recommend building it yourself, or at least attempt to, and then realize what all of the problems are going to be if you wanted to make a really slick product. So get it to the point where you've built a prototype, and then you really kind of start to deeply understand what's going on. Because a lot of times, especially with really usable products, they're really slick and they're just black boxes. And yeah, you can push the buttons and use them, but you don't end up developing a deep understanding of what's going on.
Even though hopefully if you had to do that today, that would be easier. Could use building blocks instead of really just starting from scratch. And thankfully, I know that.
Yeah, I can give you an example. So I have an undergraduate student that I suggested trying a new method. It's jargon, but I'm sure people have heard about it. Maybe you heard about it. The Stein variational gradient descent method, which is a deterministic integration method, and it's built into PyMC. So the student can go and try that. Although it's still quite difficult for them to build the quantum mechanical models that they have to build. So first, I have them do it from scratch, and of course, it works to some extent, but it's not very efficient. And there are a lot of tricks that come up in numerics. Like what do you do if you're trying to take a logarithm and there's something close to zero, right? Then you don't want them to have to figure out all those things. So have them build it first and then go, yeah.
Yeah, basically I like that. Basically using a version from scratch that's simplified, and then when you need to go industrialize that, well, just use the tools you have already on the shelf and maybe customize them if needed. That's the beauty of PyMC, where you kind of building blocks basically that you can personalize into your own Lego construction in a way. Yeah, for sure. But that's awesome. Like, well done on doing that thing. And were you already using Python at the time, 16 years ago, when you were doing your own SMC, or was it something else?
The first version was built in MATLAB, but as you might anticipate, we ran into license issues when we ended up using every one of the entire university's global optimization toolbox licenses. And so then we thought, well, this is silly. So then we moved over to Python. Now the first, it was kind of like the transition. So we had an early version built in 2.7, and then we moved to 3.
Yeah, and SMC, I know there are also some, like you can do that, yeah, with PyMC now. So yeah, if one of your students is interested, they can contact me and I'll direct them to the persons who like doing that on the PyMC community. And you personally, do you have any specific instances to share or insights that you gained by adopting a Bayesian approach in your research?
It's hard to know, I suppose. I mean, I haven't given it a lot of thought, right? Because it wasn't like I had this problem and classical techniques weren't working for me, and then I switched over and found a particular set of Bayesian techniques that ended up working. I recommend it to people because a lot of times, especially when you're thinking about things deeply and foundationally, like what do these things mean in quantum physics? I always go back to simple classical examples and say, if you can understand this, or I guess it's a more negative thing. Like if you can't understand this, then you're not going to even have a chance at understanding the more complicated thing. So, I go back to coin tosses and I say, okay, what does it mean in the context of a coin toss? And if you don't understand it there, you're not going to understand the quantum version of it. And the the subjective interpretation of probability just makes things more natural. I mean, it gives you a framework for thinking about things that you can always build on, rather than the classical approach, which it doesn't give you that framework at all. It's just grasping at straws and saying, okay, what recipes work in this situation? And there isn't one coherent framework sitting behind it, whereas the subjective interpretation gives you that. And so you might not, it's not like it gives you a specific set of tools that you can apply in every situation, but it gives you that, that footing, that foundation that you can build upon and always have that level of comfort, philosophical comfort, saying, I understand, I know what's going on.
Let me show you how to be a good Bayesian. Change your predictions after taking information in.